Watch this timer. In real-time conversational AI, your strict computational budget is 800 milliseconds. When processing audio, cross that boundary and the interaction fails. Maintain latency below 800 milliseconds, and the machine feels like a natural human conversational partner. Exceed it, and the interaction breaks down into awkward pauses and overlapping speech. Processing a single audio stream for one user within that budget is a trivial task for modern hardware. The architectural tension arises when you attempt to process continuous streams for 1 million users simultaneously. Scaling system load acts as a ruthless forcing function. It applies immense physical pressure to the infrastructure, ensuring that hardware components and software processes will inevitably fail. At true scale, perfectly optimized code means nothing if the underlying architecture collapses under saturation. The system must survive hardware failure without ever breaking that 800 millisecond barrier. To build a system that survives, we must separate the vague concept of performance into two independent, measurable metrics: throughput and response time. Throughput measures volume. It is the sheer quantity of discrete computational requests your system successfully processes over a defined period. This visual equation defines response time, measuring latency per request. Total response time adds active processing time to inactive waiting time. Under heavy load, active computation remains fast, but inactive queuing delays rapidly expand, easily swallowing up 90% of your latency budget. Engineers often measure these delays using average response times. Averages lie. They smooth out the data, hiding systemic, localized failures experienced by users at the extreme edges of the system. This statistical distribution curve illustrates a better metric. Large-scale architecture relies on target distributions, specifically the P99 metric. You must optimize for the 1% of edge case users caught in that long, trailing spike of severe delays. This graph plots system load against response time. As load increases, the system handles requests along a predictable, flat line. Eventually, it hits a resource saturation point, where CPU or memory max out. Past this degradation cliff, response times spike vertically and throughput stops entirely. Apply this to an AI sandbox. If a speech-to-text streamer attempts to chunk audio serialization synchronously on the main thread, CPU utilization instantly maxes out. The system drops off the degradation cliff, and the 800 millisecond budget is destroyed. Performance engineering is an aggressive campaign to eliminate inactive queue wait times. Keep the P99 tail away from the degradation cliff, and latency stays manageable. Surviving the degradation cliff requires scalability, the cost-effective addition of resources to handle a growing volume of work. The simplest approach is vertical scaling, or scaling up. This involves upgrading the core CPU or RAM specifications of a single machine. Vertical scaling requires zero code changes and offers trivial migration. However, it hits a hard hardware ceiling quickly and leaves the entire system vulnerable as a single point of failure. This 3D model demonstrates horizontal scaling, or scaling out. Instead of buying a larger machine, you add discrete, parallel machine instances to a cluster. Scaling horizontally offers a near-infinite ceiling and ensures high availability. The trade-off is the immediate introduction of heavy network coordination and state management complexity. There is a third parallel axis, organizational scaling. This axis measures the feature output velocity of an engineering team as headcount grows. A monolithic codebase traps an expanding team. As more engineers commit code to a single repository, merge conflicts and communication overhead multiply, causing feature velocity to stall. Splitting a monolith into independent microservices solves the human bottleneck. When isolated teams own isolated services, both the software architecture and the organizational headcount can scale outward concurrently. Scalability is a multidimensional geometry problem. Relying entirely on hardware upgrades while ignoring horizontal and organizational axes guarantees an unrecoverable system collapse. Availability evaluates the exact probability that a service is fully functional, processing data, and accessible the moment a user requests it. The cloud industry standard benchmark is 3 nines, or 99.9% uptime. Hitting this target permits a strict maximum of only 8.75 hours of total downtime per year. Look at the formula used to estimate this metric. Availability equals mean time between failures, divided by the sum of mean time between failures and mean time to recovery. Mean time between failures tracks system durability. Because hardware limits dictate this, it is functionally fixed. Mean time to recovery measures response speed. It calculates how long it takes to detect a failure, isolate the component, and execute a repair. By relentlessly shrinking the recovery time towards zero, the formula's output is mathematically driven to 99.9%. Shrinking recovery time begins with prevention. This means deploying redundant components to eliminate any single point of failure across the architecture. Active-passive redundancy sends all traffic to a primary leader, which strictly bottlenecks throughput. Active-active redundancy shares the load across all nodes horizontally, but requires heavy data synchronization overhead. The second phase is detection and isolation. Centralized monitoring systems constantly ping instances with pull-based health checks, while instances broadcast push-based heartbeats to confirm they are alive. False positives quarantine healthy hosts due to network blips, wasting capacity. False negatives are worse. The system fails to detect a dead host, and user traffic pours endlessly into a broken node. The final phase is automated recovery. Once isolated, the system executes a rapid software cycle. It stops traffic routing, auto-restarts the dead process, and rolls back to stability. Engineering high availability requires an admission of defeat. You must assume every piece of hardware will inevitably die, and design an automated system that recovers before the user ever notices the failure. With the mathematics of latency, scaling, and recovery defined, we return to the strict 800 millisecond conversational loop constraint. This data flow schematic outlines the real-time layout. Traffic flows from the client, through a Layer 7 router, into active-active gateway nodes, and finally into the stateful orchestrator. By distributing stateful audio streams across multiple nodes, we keep the system away from the degradation cliff. Now inject a catastrophic hardware failure. Under the pressure of massive, continuous user data, an active ingress node fractures and goes completely offline. The primary connection drops. This severs the stream, triggering immediate client-side WebSocket reconnect retries to bypass the glitch. The Layer 7 router detects the timeout. It tags the dead node and immediately reroutes the incoming retry traffic to the surviving active twin node. This exact active-active failover execution forces recovery time down to near zero. The conversational state is perfectly maintained, and the stream recovers without breaching the 800 millisecond total loop budget. Observe the fully integrated AI engine operating smoothly. The load is massive, the continuous streams are stateful, and the failover mechanisms are executing silently. Performance, scalability, and fault tolerance do not operate in isolation. They are deeply interconnected mathematical variables, balancing a single, unified architectural equation. Scaling a real-time system to millions of concurrent users requires abandoning the hope that hardware will simply survive the physical pressure applied to it. The engineering mandate is exact. Aggressively isolate inevitable hardware failures, strictly eliminate synchronous wait times in the queue, and use automated redundancy to mathematically guarantee rapid recovery. Mastering these attributes yields a distributed system that refuses to degrade, no matter how hard you push the traffic load against the architecture. True architectural scale is achieved only when catastrophic hardware failure becomes nothing more than a routine, invisible background process.